Okay, everybody, let's try a couple of problems with uniform acceleration. First of all, let's talk about a race car, a Porsche if you like, and let's take a look at how to solve a problem here. And basically, I'm going to call this sample problem 2-5. And here's what we know. We've got a Porsche, and it isn't going to look like one, but this is what it's going to be. And here's what we know. The Porsche is actually moving this fast. It's moving with a velocity. The initial velocity is 100 kilometers per hour, and the driver spots a police car when he's moving this fast, and he puts the brakes on, and he brakes from moving at 100 kilometers per hour. Further down the road, he is now moving with a later velocity, which we'll call VF. He's now driver's moving the car at a final velocity of 80 kilometers per hour. This happens during a displacement from here to here. Our displacement, delta x, equals 88 meters. We want to find out a couple of things. A, we want to figure out what was this car's acceleration, and B, we want to figure out how much time did it take to decrease the speed from 100 to 80 kilometers per hour. Alright, now let's think about it. We know two velocities and a displacement, and we want to find the acceleration. What equation might work? Well, if you look at your equation sheet of the four equations for uniform acceleration, you don't know the time, but you know the two velocities and the displacement. So the equation that would pop out if you expect the equations would be equation 4. So if we look at equation 4, it's the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement delta x. Let's solve this algebraically for the acceleration. That's the preferred way to do a lot of problems for an AP course. So we basically subtract vi squared from both sides, then we divide both sides by 2 delta x, and we get the acceleration equals the final velocity squared minus the initial velocity squared over 2 times the given displacement. Now, we've got an issue here. If we want our answer for acceleration to be in these units of meters per second squared, we've got to convert these velocities to their appropriate units of meters per second. So I'll do 100 kilometers per hour. We want to basically do what's called factor label. And let's do the distance first. We know that 1 kilometer is equivalent to 1,000 meters. And what we're doing is we're multiplying the given by a fancy form of 1, which will do the unit conversion and change the units. And then 1 hour would be the next conversion factor, equals 3,600 seconds. So we set this one up like so. And if you look at this, you can see that the kilometers will cancel here, and the hours will cancel here, and you end up with units of meters per second for 100 kilometers per, the equivalent in meters per second of 100 kilometers per hour. So we take 100 times 1,000 divided by 3,600. We'll find that the velocity of 100 equals 27.78 meters per second. In a similar manner, we could convert the 80 kilometers per hour, and the 80 kilometers per hour converts to 22.22 meters per second. And I'm going to hold on to an extra digit or two in an intermediate step, so we can round at the answer at the end of the problem. Next thing to do, we've got the problem already solved algebraically. Let's do some substitution and work out a solution. So what we'll have here is the final velocity is going to be 22.22 meters per second squared minus 100. Now I'm screwing up here. Minus 27.78. Sorry about that. Minus 27.78 meter per second squared over 2 times the displacement, which is 88.0 meters. Okay, now on a calculator, what you'll notice, if we do bring out our trusty calculator and turn it on, and it will work, we hope, we'll take 22.22 squared minus 27.78 squared. When you square and then you subtract, you're going to get a negative because you're subtracting a larger number from a smaller number once you square. And what we'll get is that we have minus 278, and that's going to be meters squared over seconds squared. We're going to divide that by 2 times 88. Okay, divide that by 2 times 88, and 2 times 88 gives us 176 meters, an intermediate step here. And once we take the minus 278 minus 278 divided by 176, we'll see that we get an acceleration that A equals a negative 1 point. Let's go with 3 sig figs because let's assume our givens. Let's go with 3. This would be 1.5 minus 1.58, and the units. What will happen with the units? You have meters squared over seconds squared divided by meters. The way that works, I'll show you up here. This would be meters squared over seconds squared. Instead of dividing by meters, we're going to multiply by 1 over meters. And the meters is going to cancel, 1 on the top, the 1 on the bottom, and you're left with meter per second squared, your acceleration units. So we got our acceleration is minus 1.58 meter per second squared. That's the acceleration of the Porsche. It's slowing down at a constant rate. It's losing this much speed, 1.58 meter per second. If you think about these units, again, you can think about it as meters per second squared. But the other way to realize how it's working with units before they're simplified or condensed, it's losing minus 1.58 meter per second for every second that it slows down. Okay, so keep in mind when the units are compact, they kind of don't give you the story of what's going on once you expand the units back to meter per second per second. Okay, part B, everyone, we want to figure out the time it takes for this to happen. So part B, we want to figure out the time. Now to get the time, what we're going to do is we've got the 2 velocities, we've got the displacement, we now have the acceleration. There's a couple of different equations to use. I believe equation 2 would be the way to go. Equation 2 is the final velocity equals the acceleration times the time plus the initial velocity. And we're going to solve this algebraically for t. First we're going to subtract vi from both sides, and then we're going to divide both sides by a, so the time will equal final velocity minus the initial velocity over the acceleration, which we just figured out in part A. Let's do the numbers. The final velocity, once again, this is 22.22 meters per second minus the initial velocity, which is 27.78 meters per second, divided by our newly found acceleration, which is minus 1.58 meter per second squared. And doing some of the math, again using the graphing calculator, we have 22.22, I know you can't see those numbers very well. There we go, that's a little better. 22.22 minus 27.78, we will get minus 5.56 So this is minus 5.56 meter per second. That's the delta V, the change in velocity, divided by the rate at which the velocity changes, which is the acceleration, which is meter per second if you like. And we do the division. We take minus 5.56 divided by minus 1.58, negative 1.58, and we get a time of 3.52 at round 2. So the time equals 3.52. Now, do we get the desired units? Well, they should be seconds, and let's confirm that they are. So to do the units up here, this would be meter per second on the top, and we're dividing by meter per second, or meters per second squared, which is the same as multiplying by seconds squared over meters. I'm taking the reciprocal units. The meters will cancel. Seconds on the bottom cancels one of the seconds on the top, so we are left with units of seconds, which is fine. So it takes this event 3.52 seconds. Now you have to ask yourself, does this person who's allegedly speeding, do they get the car slowed down before the cop has time to shoot the radar gun at them? Well, a radar gun can be operated pretty quickly, and I think if the policeman knows what he's doing, they'll definitely clock you moving. You might be mid acceleration or deceleration, or negative acceleration, which is the preferred way to say it. They have time. If the speed limit's 80 kilometers per hour, they have plenty of time to clock you moving faster than that, even though you are slowing down. So I guess the lesson here is you don't have as much time as you think you do. 3.5 seconds is a long time if the cop has you in their sights, so to speak, even before you slow down. You can just add to the 3.5 seconds that they have time to catch you speeding and possibly, get a ticket.